Assalamualaikum and good day to everyone. So we continue our lecture with chapter 5, which is transmission line. What we have learned before, if we want to transmit a signal from transmitter to receiver, we need a transmission medium. So the transmission medium, we have two types of transmission medium, which are wired and wireless. For the wired transmission medium, we also call it transmission line. So transmission line include variety means such as metallic cable, optical fiber, and the goal for transmission line is very simple: is to transmit the energy of a signal from a source at one point to a load at another point with very little loss. So we know that signal is kind of is also an energy. So transmission line is used to transfer the energy, in other words, the signals from transmitter to receiver with very little loss. There are two choices for transmission lines, which are coaxial line and open wired parallel line. So this picture shows the coaxial line. So biasa kita lihat ini di kalau ada menggunakan wire Astro, so wire Astro menggunakan coaxial line, and this picture shows the parallel line, the open wire parallel line. So normally we use for antenna. So kalau TV lama yang menggunakan antena, biasanya akan menggunakan this type of wire. In general, there are two types of transmission lines, which are balanced or unbalanced transmission lines. So we'll go further what is balanced or unbalanced transmission line. As mentioned in the few slides before, we have two choices of transmission lines, which are the coaxial line and the open wire parallel lines. In physical, perbezaan antara kedua itu adalah coaxial line dia hanya ada satu wire, whereas the open wire parallel line dia ada two wires. So it's a pair, it's a two wire transmission lines. So for balanced transmission line, it refers to the two wire transmission lines, which is the open wire parallel line. So this type of transmission is called difference or balanced signal transmissions. So you can see in the figure 4.5. So what's the advantage of this balanced transmission line is that since it has two wires, so if there is noise in these two line, it will cancel each other. The following slide you will understand better. So in other words, this balanced transmission line can reject or minimize the noise interference. So as I mentioned, apabila ada noise pada kedua-dua wire tersebut, maka ia akan cancel each other, and it also called common mode rejection. So gambar ini this is the twisted pair or the open wire parallel line. So seperti yang saya nyatakan sebelum ini, bahawa jika ada wujudnya noise pada kedua-dua belah wire tersebut, maka ia akan cancel each other. Sebagai contoh di atas kita ada noise di sini dan kita ada noise di sini dua tempat. So ia akan interact dan cancel each other, and this noise will be eliminated, will be disappear. So same as this noise and this noise, so it will interact and cancel each other. The same goes to this figure. So you can see there is a noise here and also noise here, so it will interact and cancel each other. So the good of balanced transmission line is that when there is a noise in both wires, they will cancel each other, and eventually the noise will disappear. Another way, we have unbalanced transmission lines. So why we call it unbalanced? Because it only has one wire at the ground potentials, whereas the other wire is at the signal potentials. So this type of transmission line, we call it unbalanced signal transmissions. So the advantage of this kind of transmission line, because it's only one, so the cost will be lower than the open wire parallel line. But the primary disadvantage of this unbalanced transmission line is that it reduces the immunity to common mode signals such as noise and other interference. Berbeza dengan balanced transmission line, if there is a noise in both wires, it will cancel each other. But for unbalanced transmission lines, since it only has one wire, so it cannot cancel the noise. If there is a noise, the noise cannot be cancelled because only one wire. So the following figures shows the unbalanced and balanced transmission systems, so it will be easier for us to understand it. So this diagram shows the unbalanced circuit where it only has one wire that connects two devices, and this is the balanced circuit. It has two wires that connect two devices, and this is the example of the unbalanced transmission line. It's a coaxial line, and this a pair wired for a balanced transmission line. Now we learned about the electrical characteristic for the transmission lines. So in that case, there are three parameters that we need to understand about the electrical characteristic for transmission lines, which are the characteristic impedance, velocity factor, and the standing wave ratio, SRR. So we learn in details of each. First is characteristic impedance. In this lecture, I will not explain to you in detail what impedance is. I assume that you already learned before. Anyway, the following video will help you to understand more about impedance. So characteristic impedance is the impedance of the transmission line. So we know that transmission line is function to transmit the signal from transmitter to receiver. It's like the mechanism. So we need the mechanism of how the signal can be transmitted. So in the concept of characteristic impedance, we see that the transmission line, or the physical transmission line is actually a series of circuit that connected from transmitter to receiver. So that's how the signal or the energy of the signal can be transferred from transmitter to receiver. So for the maximum power transfer from the source to the load, or no reflected power, a transmission line must be terminated in a purely resistive load equal to the characteristic impedance of the transmission line. What it means, if the receiver, if the impedance of the receiver is the same as the characteristic impedance of the transmission line, so the receiver can fully absorb or receive the power transmitted from the transmitter. So power means the energy of the signals. In other way, if the impedance if the load impedance at the receiver side is equal to the characteristic impedance of the transmission line, so the receiver will receive all the signal transferred from the transmitter. So the figure 5.9 will show you a section of a transmission line terminated in a load ZL equal to the characteristic impedance.
Hello again, ladies and gentlefolk. It's time to discuss a new concept in LCR circuits. Although in retrospect, you should realize that it's not a new idea at all. What I'd like to go over is this thing called impedance. We know that an LCR circuit contains a resistor, a capacitor, and an inductor. In previous modules, we looked at each of these components in detail, and perhaps you noticed what they all have in common. All the components in the circuit have some slowing effect on the electricity that flows through them. They all show some kind of opposition to the current provided by the power source. You see, a resistor is designed specifically to limit the current in a circuit. It resists, it's in the name. A capacitor collects charge from the circuit in a way that makes it very hard for current to flow through it. Remember, a capacitor consists of two conducting surfaces that are separated either by air or by a dielectric layer. And an inductor, according to the laws of Lenz and Faraday, opposes any change in the amount of current through it. This you should be familiar with by now. So if you take each of these components and plug them into a source of alternating current, as I've done here, they all oppose or impede the current. Current flows into the resistor says, "Not so fast there," and it acts a bit like a toll booth. Then current tries to go through the capacitor, but the capacitor says, "Nah, you ain't going nowhere," and it starts to charge up. Because we use AC, the size of the current is changing all the time. That creates a changing magnetic flux in the inductor, which induces a countercurrent. All these opposing effects contribute to the impedance of the circuit. Impedance is found by taking the resistance of the resistor and adding it to the reactances of the capacitor and the inductor. But it's not as simple as adding three numbers and pushing the equals button. This is the phasor diagram showing those three quantities. Notice they all point in different directions and do not line up. In fact, each reactance phasor is at right angles to the resistance phasor. Therefore, we have to use vector addition to add them all up. If you have never seen vectors before in your life, I suggest you pause this video right now and go over to the mechanics section. Phasors are defined as vectors which rotate, so their directions are important. Luckily, finding the impedance becomes very straightforward once you understand how to add these phasors up. First, we can subtract one reactance from the other. This is because the inductor and capacitor have reactances with the opposite phase. They are exactly 180 degrees apart. So take the smaller one away from the bigger one to get a new vector, the net reactance, if you will. Now, the reactance is at right angles to the resistance phasor, so we have two sides of a right-angled triangle. That impedance we're looking for is the third side of the triangle. What do we do with right-angled triangles, folks? We use the theorem of Pythagoras. Now you take your calculator out and use this fantastic formula. I'll run through a quick demonstration so you can see the whole process. Suppose our capacitor has a reactance of 10 ohms, and our inductor a reactance of 6 ohms. The resistor is a pretty skinny one, rated at 5 ohms. Here's what it looks like when we plot that data on the phasor diagram. The capacitor has a larger reactance than the inductor, so we take the smaller one away from the larger and get this. Now we have two sides of a right-angled triangle, and the impedance is the hypotenuse. I'm going to use the Pythagoras theorem, and I'd like you to watch the working steps closely. and the answer comes out as 6.4. Impedance is still measured in ohms, so that is 6.4 ohms for this particular LCR circuit. Good show. To recap, impedance is the total opposition to the flow of electric current in an LCR circuit. It is found by taking the vector sum of all the resistances and reactances that can be measured. In our equations we give it the symbol Z and measure it in ohms. That is all you need to know for the next series of exercises.
So I hope from the previous video you understand what impedance is. So as mentioned before, we know that the transmission line looks like a series of circuits. Okay, so as also mentioned before that the maximum power can be received by the receiver. This is receiver side. This is transmission line. This is the transmitter side. Okay, this is the impedance of the load impedance at the receiver side, and this is the characteristic impedance of the transmission line. So in order for the receiver to fully receive the energy from this transmitter, the characteristic impedance of the transmission line must be the same as the load impedance at the receiver side. So if that case, all the power can be fully absorbed by the receiver. So as mentioned also that the transmission line look like a series of circuits. So this is the one section of the circuit, one unique length of the circuits. Okay, so it's one set. The one set of the circuit look like this. So actually for the long transmission line, it contains of a series of sets. Okay, not only one set but more than one set. And this is what I refer about the series of sets. So this is in this picture it shows that series of sets that connect between the transmitter to receiver. So this slide shows the derivation of the characteristic impedance. So you don't need to understand or to know in details about the derivation. What the important thing is how we use or understand the formula. So from the derivation, we finally know that this is the formula to determine or calculate the characteristic impedance. So there are two types of formula. So this formula is used for low frequency, and this formula used for the high frequency. Normally we'll use for this formula in the case of high frequency. As described in the early chapter, we know that transmission line contains of two types of cable, which are coaxial cable, coaxial line cable, and open wire parallel line cable. So characteristic impedance also can be determined or calculated based on the physical value of the cable. So this formula is used to determine the characteristic impedance for two-wire parallel transmission line. So we see that D represents the distance between the centers of the two conductors. We know that two-wire parallel transmission contains of two wires. So D is the distance between the two wires, and small r is the radius of each conductor or the wire. So this figure shows, figure A shows the physical value of the two-wire parallel transmission line. So we know that it contains of two wire. So D is the distance between the center of these two wires, and R is the radius of each of the wires. And B is the coaxial cable transmission line, where it only one cable. So D is the diameter of the cable, and small d is the inner diameter of the cable. So epsilon r is the dielectric constant of the material. So this is the formula how to calculate the characteristic impedance for the coaxial cable, as mentioned in the previous slide. So D is the diameter of the insulating materials, small d is the diameter of the inner conductor, and epsilon r is the dielectric constant of the material. So based on this value, we can determine or calculate the characteristic impedance of the coaxial cable. So let's see an example. A piece of RG559BU coaxial cable has a 75 ohm characteristic impedance and a nominal capacitance of 65 picofarads per meter. What is its inductor per meter? If the diameter of the inner conductor is 0.584 mm and the dielectric constant of the insulation is 2.23, what is the outer conductor of the diameter? So first we extract what the information given from the question. So first it gives the value of characteristic impedance, which is 75, and capacitance of 69. So from these two information, actually we can define the we can identify or calculate the inductance. So this is the formula of how to calculate the characteristic impedance when the inductance and the capacitance value is given. So since the characteristic impedance value and the capacitance value is given, so we can find the C. So as mentioned before, this formula is used to identify or to calculate the characteristic impedance for the case of high frequency. So just bear in your mind that if there is no mention in the question whether it is for high frequency or low frequency, we assume that it is for high frequency, unless if in the question is mentioned for the low frequency, then we use the formula for the low frequency. Okay, so we assume this for the high frequency. So from the given value, from the given information, we can identify or calculate the inductance. So finally the inductance is 0.388. So based on the calculated value that we find here for the inductance, so next we'll need to calculate the outer conductor of the coaxial cable. So based on the question, we are given the value of inner conductor, and the dielectric constant of the material is 2.23. So this is the formula to calculate the characteristic impedance for coaxial cable. So we are given the value of, we already know the value of this characteristic impedance. We also given the value of the dielectric constants and the inner conductor value, which is 0.584. So now we need to find the outer conductor diameter, which is the capital D. So we just plug in the value, and at the end we find the value for the conductor diameter is 3.77 millimeter. Next is the velocity factor. We know that we need to transfer the signal from the transmitter to receiver. The signal itself is a kind of energy. Okay, so the velocity of the energy at in the free space is like the same velocity of the light, which is about 2.98 to the power of 10 times 10 to the power of 8. Okay, however, the velocity of the energy or the signal is not the same when it goes to the physical materials. So a velocity factor is defined simply as the ratio of the actual velocity of propagation of an electromagnetic wave, which is the signal, given in medium to the velocity of propagation through a vacuum or free space. Okay, so this is the formula of velocity. It's actually the ratio between the velocity of the signal through the certain medium compared with the signal when it transferred through vacuum or free space. So in the free space, the velocity is assumed as the speed of light, but in the medium, it slower than the velocity of the speed of light. This VP, or the velocity of the signal in the certain medium, can also be calculated from a given value of inductance and capacitance. So by the way, the velocity factor also is the value of velocity factor from derived from this value is quite similar or close to the value of when it gives the value of dielectric constant. Okay, so if we calculate the velocity factor based on this value, and we also can get the similar value when we use the value of dielectric constants. So let us see an example for calculating the velocity factor. For a given length of Rg 8a coaxial with a distributed capacitance of C equal to 96.6, a distributed inductance L equal to 241.56, and a relative dielectric constant of 2.3, determine the velocity of propagation and the velocity factor. So this question is actually want us to calculate the velocity factor using the inductance value and the capacitance value, and compare with the velocity factor determined by this dielectric constant. So first we calculate or determine the velocity factor based on the inductance and the capacitance value. So based from the formula given, so we plug in the value, so at the end we got the velocity factor is 0.69. So next we calculate the velocity factor using the information of dielectric constant. So when we plug in the value, then we got the value of 0.66. So based on these two values, we can see that the velocity factor derived from the value of inductance and capacitance is quite similar, or the same the value of velocity vector when we calculate it based on the dielectric constant value. So it's quite close. So as explained before, we know that when the characteristic impedance, the load impedance is equal to the characteristic impedance, the receiver can absorb or receive all the energy from the transmitter. We call it a mesh transmission line, where the load impedance is equal to the characteristic impedance. But when the load impedance is not equal to the characteristic impedance, so the receiver will not receive all the energy from the transmitter, and only a part of the energy can be absorbed or received by transmitter, and others will be reflected back. So when it happens, we call it unmatched transmission line. So when the load impedance is not equal to the characteristic impedance, some of the energy will be reflected back to the transmission line, not being absorbed by the receiver. So we call it a standing wave, where the signal or the energy is reflected back from the receiver to transmitter. So this figure shows how the standing wave appear. So the first is shows the incident wave, where the wave from the transmitter to receiver. Then in B it shows the reflected wave. When the case of load impedance is not same as characteristic impedance, so all the incident wave cannot be absorbed by receiver. So some of the wave will be reflected back. So this is the reflected back, or we call it reflected wave. So when it happens, so the incident wave and the reflected wave will collide and will meet each other, and it will become a standing wave. So standing wave is the output of the incident wave and the reflected wave. So this standing wave has its maximum value and minimum value. Standing wave ratio. What is standing wave ratio? Standing wave ratio is the ratio of the maximum voltage to the minimum voltage of the standing wave on a transmission line. As explained in the previous slide, we know that standing wave is the output of the incident wave and the reflected waves. So these two waves combine and it become a standing wave. So standing wave contains of the minimum and maximum value. So standing wave ratio is the ratio of the maximum and the minimum value of the standing wave on the transmission line, and it also called a voltage standing wave ratio, VSWR. So this formula shows of how to calculate the standing wave ratio. We know that it's the ratio between the maximum value and the minimum value. So how to calculate the maximum value of the standing wave? So the maximum value of the maximum is the sum of value of the incident voltage and the reflected voltage. We know that the standing wave is the combination of the incidence wave and the reflected waves. So the maximum standing wave value is the combination of the value of incident voltage and the reflected voltage. So for the minimum value is the difference between the incident voltage and the reflected voltage. Voltage standing wave ratio is also can be defined based on the reflection coefficients. So reflection coefficient is determined as the ratio of reflected voltage to the value of incident voltage. So from here we can rearrange the value of this and can be written in the reflection coefficient manner. So at the end, so voltage standing wave ratio can be represented by these reflection coefficients. And once we got this, and then we rearrange back, so the reflection coefficient can also be written as this. So let's see the example for standing wave ratio. For transmission line with incident voltage EI equal 5 volts and reflected voltage equal to 3 V, determine the reflection coefficient. So based on these two values, we actually can determine the reflection coefficient and also the standing wave ratio. So first we calculate the reflection coefficient, and we got a 0.6. And based on this two value, we also can determine the standing wave ratio. At the end, we got the value of standing wave ratio is 4. So based on this value, is actually can calculate the reflection coefficient. So when we plug in this value into this formula, at the end we got the value of 0.6. So it's same as this value. So it shows that the reflection coefficient can be determined based on the value of incident voltage and also the reflected voltage, and also the reflection coefficient can also be determined based on the value of standing wave ratio. So what is these are the disadvantages of having unmatched transmission line. We know that standing wave is originated based on the reflected wave that not being absorbed by the receiver. So when it does happen, so it means that 100% of the source incident power is not absorbed by the load. So only some of the power is being absorbed by the load or the receiver, and some of it is reflected back. So when it happens, so it may cause more power loss. So some of the reflected energy will be lost, and it also can the reflected wave can also be will interfere with the incident wave. So this may cause mismatch. So next is Smith chart. We know that when the load impedance is not the same as the characteristic impedance, it will cause the standing wave. So the standing wave is not good for a system. So in order to avoid this, we have tools what are called Smith chart. So this Smith chart will help us how to find the proper we call input impedance. So input impedance something value that will balance the output at the output side. So now we have three type of impedance, which are characteristic impedance, load impedance, and input impedance. So all these three impedance must be balanced, so that the output the system will be function better. So Smith chart is a tool that was developed by a man called P.H. Smith in 1930s, and actually the Smith chart is a powerful tool that can do many things, can give us or to help us in many things in designing system. But based on the on our lecture, we only emphasize the Smith chart to find the voltage standing wave ratio and also the input impedance. So this is how the Smith chart looks like. So it looks like a complex graph. Actually, what you need to understand is that in this Smith chart, there are two types of lines. First is the circle here. Circle. There are many circles lines. Let me write. Okay. You can see that there are many lines. Okay, many cycles in this chart. Okay, and also we can see that there's another types of lines, this line. Okay, so bear in your mind that there are two types of lines, the cycle lines and this kind of lines. So what are they? So the circle lines is the real impedance, and this line represent the imaginary impedance. So what are they? So we will go further in details in the following slides. Before you want to use the Smith charts, so these are the tools that you need to have in order for you to use the Smith charts. So we have this, we call it compass needle, or inverser, I think Jankelukis. Okay, so we need a protector and also we need a ruler. So make sure you have all these three tools in order for you to Smith chart. So if you miss one of them, you can properly use the Smith chart. So make sure you have all these tools. As I explained before, we have many circles in that chart. So the circle actually represent the real impedance value. Okay, so the value goes to the right and goes bigger to the biggest, go bigger to the right. Okay, it start from here to here, and towards the to the right, the value of the circle is higher. And this kind of lines represent the imaginary impedance. Okay, so these lines we have two types. We have the upper and we have the lower side. The upper side is the positive. positive lines, and for the lower part is the negative value. So let us do some exercises of how to plot on the Smith chart. So normally we will given a value of characteristic impedance and also a load impedance. Okay, so in this exercise you are given the value of characteristic impedance of 50, and you have a lot of value of load impedance. So first, before you plot on the Smith chart, you need to normalize the value. So how to normalize the value? We need to divide the load value to the characteristic value. So these are the values that have been normalized based on the upper value. Okay, so this value is actually the output, the value based on this load impedance divided by the characteristic impedance. So these are values that you can use to plot it on the Smith chart. Okay, so let us see for the first plot. So for the Z1 is equal to 2 plus J. J means 1J. This is the positive imaginary impedance. Okay, so first we need to find these two on the real impedance circle. So for the Z1, so this is the line for the real impedance. The value of this real impedance circle is 2. Okay, and then we need to find the value for one imaginary impedance. So if you see closely to the chart, you can find that this line is actually the line that has the value of 1. As I mentioned before, the upper part is for positive, the lower part is the negative. So since it is the positive 1, so we see the upper lines. So this line is the line for the imaginary part, which has the value of 1. So we can see here we have this line, and then first we have this circle line of value of 2. Okay, so how we can plot? We see the intersection part of this circle line and this line. So the intersection point for these two lines are here. So here is the value of 2 plus 1J. Okay, so you can do some exercises based on this value, see whether you get the plotting the same as in this example. So make sure you do these exercises and make sure you can find you know how to plot the value on the Smith chart. So as mentioned before, in this lecture we only we use the Smith chart focusing on to find the input impedance and voltage standing wave ratio. So what is input impedance is actually, we know that load impedance is the impedance at the receiver side. The characteristic impedance is the impedance of the transmission line, and input impedance is actually the impedance at the transmitter side. So based on this, we need to find the proper input impedance so that this whole transmission line system will be function properly to minimize the standing wave. So the distance between the transmitter and receiver, we represent it as a value of lambda. Okay, so this is only the example. Okay, so we know that lambda is the value of length of the signals. Okay, so we also know that the unit of lambda is in meter. So that's why we represent the distance between transmitter is in lambda. So at the end we got the value, something value that's in meter. Okay, so the lambda, it depends on the system, what the frequency used for this system. So the lambda is the frequency that being used in the system, the frequency of the carrier normally. Okay, so we go through the example based on this value. Okay, so then we know how we can use the Smith chart to find the input impedance and also the voltage standing wave ratio. So I hope you understand this example, so that if you understand, so it's easier for you to understand for the next step of how to find the input impedance. So this slide and the following slide is actually show you the procedure of how to determine or how to calculate the input impedance and also the voltage standing wave ratio from the given value in the example. So I will not explain in details one by one the step in this slide and also the following slide, but I will explain the summary on the solution chart. So in the example, we are given the value of load impedance 37.5 and characteristic impedance 75 ohm. So first, as I mentioned before, first you need to find the normalized value, the normalized impedance value. So how to calculate the normalized impedance value? You need to divide the load impedance divided by the characteristic impedance. So finally we got the normalized impedance is 0.5. So so you know how to plot the 0.5 value on the chart. So based on the exercises you probably you have done before, so you know that the value of 0.5 is here. So from here, after you got the plot here, so then you need to write a circle. Okay, so circle based on the center. This is the center of the chart or the Smith chart. So cara untuk awak buat circle adalah dengan menggunakan jangka sudut. So pastikan sudut tajam ataupun jarum jangka sudut anda berada di betul-betul di tengah-tengah chart ini, and then menggunakan jangka sudut tersebut, draw this line. So draw this circle line. Okay, so once you get this circle line, then you see this line. Okay, so based on the intersection between the circle line that you have drawn, and the straight line on the Smith chart, so you can find the intersection point here. So what it means, so this intersection point is actually the value of standard wave ratio, or VSWR. So we can see here, if you closely see this chart, you can find that this point is the value of this point is actually 2. So value of 2 is the standing wave ratio. So now you already know that this circle will give you the value of standing wave ratio when it intersect with this line. Okay, so any value that intersect in this line on the left side, okay, the left side, so assume that this is the left side, so this is the right side. So any circle that intersect with this line on the right side, so that circle is considered the intersection point based on these two lines is considered as the standard wave ratio. So now you already get the value of standard wave ratio. So next, what is next? Next, we need to find the input impedance. Okay, so we know that the distance between the transmitter and receiver is 0.125 lambda. Okay, so before that, one thing I need you to know is that if you closely see this Smith chart, later on I will give you the file of Smith chart, then you can look closely to the Smith chart. So if you see the Smith chart, you can find that the outer value, okay, the outer value is actually the represent the lambda value. Okay, so for one cycle, value, one complete cycle value is about 0.5. Okay, 0.5 lambda. Let me write on the screen. So the complete cycle, it should start from here and end at this point. So the complete cycle represents 0.5 lambda. Sorry. It's correct that one cycle is equal to 0.5 lambda. So the question is that the distance between the transmitter and the receiver is 0.125 lambda. So since one complete cycle is 0.5 lambda, so 0.125 lambda is actually a quarter of the cycle. Okay, so as you can see here, the quarter of the circle is here. Okay, so you find that the value of 0.125 lambda from here, from this point, it will go until here. So you got the value of 0.125 approximately here. So what is next? So once you get this point, the distance, which is the distance between the transmitter and receiver, then you need to draw a straight line from this point to this center. Okay, so you got this straight line. Okay, so this straight line, this straight blue line. Okay, so after that, once you got this straight line, so you see the intersection point between this line and the circle line that you have made before. Okay, so this is the circle line for the normalized impedance. Okay, so this is the line that you have made based on the distance between the transmitter and the receiver. So you got this line. So then you see the intersection point between this circle line and this straight line. So what does that mean? So this point is actually the normalized input impedance value. Okay, so the normalized input impedance value. So from based on this example, you will see that the normalized input impedance, so this value, this point, the value of this point is 0.8 plus j0.6. okay, so this is the value of normalized input impedance. So how to calculate the input impedance? So to make it input impedance, so you need to multiply this normalized input impedance with the characteristic impedance. Okay, so the characteristic impedance is 75. So if you multiply this value to the characteristic impedance value, so you will get the input impedance value. So bear in your mind, this value is not input impedance. This is the normalized input impedance. So once you multiply it with the characteristic impedance, then we will get the value of input impedance. hope you understand this example. So let's say, what if the case, the distance between the transmitter and receiver is let's say 1.125 lambda. Okay, so what if the case, the distance between the transmitter and receiver is 1.125 lambda? So you know that for one complete cycle, the lambda value is 0.5. So when it 1.125, so first you need to circle it twice. So if for the second circle, the when you go to the second circle, it means that you already complete one lambda. Okay, so first 0.5, second 1.0 lambda. So to complete 1.125 lambda, so you need to go until here, because from here to here is about 1.25 lambda. So two cycles plus this length, so you will get 1.125 lambda. So basically it's the same value as 0.125 lambda. So bear in your mind, don't make confused if you need to go many cycles to get the full value of the distance. Okay, let's do this example. Okay, determine the input impedance and value the voltage standing wave ratio for a transmission line 1.25 long with the characteristic impedance equal 50 ohm and the load impedance equal 30 plus j40 ohm. Okay, so I just give you a tips that this 1.25 lambda, based on the Smith chart, you need to go two cycles. You get 1 lambda, and the rest 0.25 lambda is actually half of the circles. Okay, so then you get the point where you can find the input impedance later on. Okay, so just to remind you, to recap the procedure. First, you need to find the input, the normalized impedance. So the normalized impedance, you need to divide this load impedance with this characteristic impedance, and then you get the value. So from this the normalized value, you need to plot on the Smith charts. Okay, so then once you get the plot on the Smith chart, you need to develop to make a circle based on this plot. So the circle is where the center of the circle is the center of the Smith chart. So you got the circles. So once you get the circle, so you can find the voltage standing wave ratio, where the intersection point of the circle that you just made with the straight line, the straight line on the Smith chart. So the voltage standing wave ratio is the intersection point of these two lines. Okay, and then once you get that, so you need to find the input, the normalized input impedance first. So how to find the normalized input impedance? First you need to see the distance between the transmitter and receiver. So it gives that the distance value of transmitter between the transmitter and receiver is 1.25 lambda. So based on the Smith chart, you need to find the distance that represent this, and then once you get the point at the outer circle of the Smith chart, then you write down, you draw a straight line from this point to the center of the Smith chart, and then the intersection point from this just you just through the line with the circle line is the is the normalized input impedance value. So this is the solution looks like when you got the right point and the right circle and the right points that you already did. Okay, so make sure you understand this example. So please practice by yourself and try to find the right answer. So if you got this answer based on your understanding, so it can be say that you understand the example. So please again try to make such exercises and try to understand the example that I have explained to you. Okay, perhaps this question might be one of the question in the final exam. So, but it's not straight as this example. So, but you first need to really understand of how to use the Smith chart to find the input impedance and the voltage standing wave ratio. Okay. Till then, so this is the last last lecture. So hope you can understand all of my recorded lecture. If you have any question, you can ask me, or whether you can ask Dr. Huda. So anyway, good luck for your exam, and I pray for the best of you. Thank you very much.